So to more academically define it, we are gonna define math literacy like this. The ability to apply math concepts and knowledge to solve real-world problems and communicate solutions with others. So this is the main concept that we want to promote in math education. And one of the ways to promote math literacy is through mathematical discussions. So because we use mathematical discussion to promote math literacy because it requires students to explain their thinking process, exchange possible solutions, and justify their reasoning. Then what is the relationship between math literacy, language skills, and linguistic features? Math literacy is not just about numbers and symbols, but about understanding the meaning and communicating with others using language. More specifically, shared math language. So lower language skills can present critical obstacles in math reasoning, and also the use of language to communicate math knowledge can enhance students' math skills. So we are gonna the thing we are interested in is linguistic synchrony, which is the degree to which two or more speakers share linguistic properties such as lexical choices in dialogues. And linguistic synchrony is also known to be correlated with better collaborative task performance, common knowledge building, and learning gains. So here are our research questions. First, what are the characteristics of linguistic synchrony in mathematical discussions? And second, what is the relationship between linguistic synchrony and math literacy? To answer those questions, we use those methods. Our data came from MathNation, which is an online math learning platform for middle school and high school students. And in MathNation, we have a discussion forum that students can I use this? Oh, yeah, okay, sorry. It just restricts my movements, okay. So that students can post their questions about math problems, and the facilitators can answer those questions by replying to the post. So we extracted more than 20,000 threads of discussions, and this is the data that we use for our analysis. Before we dive into linguistic synchrony, we have to measure students' math literacy based on the discussion. If you remember the research question 2, it was the relationship between math literacy and the linguistic synchrony. So we wanted to see how the students' math literacy looked like. So we developed a rubric like this. Based on the previous literature, we had 3 constructs of math literacy, which are knowledge and content, competency and skills, and application in the real world. Knowledge and content is the ability for students to understand math concepts and giving correct answers. Competency and skills is the ability to communicate using math terms and math formulas. And the application in the real world means the student's ability to connect math concepts to interpret the real world problems. So we have this rubric of high and low and the descriptions and examples. And based on this, we manually annotated over 700 threads. So we, for the initial 200 threads, 2 raters independently evaluated the 200 threads, and then the kappa score was above 0.85. So this is how the evaluation looked like. So we have a list of threads, and we have 3 constructs, and we gave them either 0 or 1, and we have this overall math literacy by summing those 3 construct scores. For example, if the score is 2 and 3, that means it's high math literacy. And if the score is 0 or 1, that means it's low math literacy. So because we have like 20,000 discussion threads, we had to automate the assessment of math literacy. So for the remaining discussion threads, we use a bunch of text classification models. So out of those models, we chose the ones with highest accuracy, with these bolded ones. So for these two constructs, we use the long former, and the last construct, we use BERT model. And then, before we actually go into the linguistic synchrony, we did some pre-processing. So we had multiple facilitators in one thread, right? So, but we didn't want to differentiate those facilitators, so we grouped them into just one facilitator's audience. And we did a lot, like other pre-processing for the language, such as lowercasing, removing punctuation, stop words, like that. And then, to measure the linguistic synchrony, we use Cross-Recurrence Quantification Analysis, that's CRQA. It is an extended family of RQA, which is Recurrence Quantification Analysis, that is a data analysis methodology that quantifies the repetition of data points within a series data or numerical data. So this is how typical RQA looks like. So we have a series data, and we want to see how this data is repetitive. So so this recurrence plot is the outcome of RQA analysis, and it marks all the points that the data revisits the points that it already has been. So if you see this like regular time series pattern, and that's why this looks like a very regular and predictable recurrence plot. But what we're using is language data, right? So we had to convert the language data into numerical data. So this is an example of how to convert language to numerical data. So for example, this sentence like imagine an imaginary manager, imagining, managing, and imaginary manager. So we have 2, 3, 4, and 8, 9, 10 repetitive, right? These three phrase, like these three words of this phrase of three words is repetitive. So we can check those repetitive points, and this is how the RQA looks like. In our analysis, more specifically, use CRQA as opposed to RQA. So CRQA looks like this. So this is an RQA plot. So as we can see, we have X and Y axis with same X and Y axis. That's why it has a long diagonal line and it has the symmetric pattern. But for CRQA, we don't necessarily use the same X and Y axis, which allows us to calculate the synchrony between two data sets instead of the repetition within one data set. So in our case, x-axis will be like students' utterances, and the y-axis could be facilitators' utterances. And this is another output of CRQA analysis. We have 5 indices, which is like RR stands for recurrence rate, which is the percentage of recurrence points out of all possible points in the recurrence plot. I will show you with an example in the next slide. DET means determinism, which is the proportion of recurrence points constructing diagonal lines out of all the recurrent points. So let's say there's a like conversation between students and the facilitator. The student says, how do similar polygons have what do similar polygons have the same number of? And the facilitator says, if they are similar, they should have the same number of sides and angles. So we have, after preprocessing, we will have those keywords. So similar, polygon, number, and $sign, which is a placeholder because we have different number of keywords here. So we just put the $sign as a placeholder to make it square. And we have similar, number, side, and angle. So those similar and number are synchronous between those two speakers, and that's why we mark those points in the recurrence plot. And this is how we calculate recurrence rate. So we have all the possible recurrence, so we have 2 points marked out of 16 possible recurrence points. So that's why we have 2 divided by 16, 12.5% of recurrence rate. So let me show you our results and discuss. So this is the characteristics of linguistic synchrony in math discussion. So we have recurrence rate of 0.73, which is less than 1%, which is, if I compare to previous research, this is pretty low number. And the DT is also lower than the previous research, and we have the very relatively high standard deviations. And the relationship between linguistic synchrony and math literacy. So we compared those high literacy group and the low literacy group with this Mann-Whitney U-test. So we have overall and 1, 2, 3, like 3 sub-constructs. So to represent, I'm gonna just look at the overall results. So if you look at this Z-score, we can see the relationship, like if it's positive or negative, like which one is bigger. So for these 3, we have high literacy group has a bigger figures of these indices. So recurrence rate and the number of line and the average length of the line, diagonal line, is bigger in high literacy group, which we can conceptualize as linguistic concurrence. And we have this negative Z-score of the determinism. So that means low literacy group has a bigger determinism, and we can conceptualize it as predictability. And this is another negative score. So entropy is a normalized entropy. That's also like lower literacy group has a bigger entropy. We can interpret this result like this. The student with high math literacy tend to have a higher linguistic concurrence, which is they share the same words, same sequences, and longer sequences with the facilitators. And students with high math literacy also tend to have smaller predictability, which means they are less likely to repeat the sequence of the words the facilitator says, but rather paraphrase them. And the student with high math literacy tend to have smaller complexity, which means they use more uniform number of overlapping words, rather than either neglecting the necessary terms or repeating the whole sentence, which students with low literacy would do. So this is a result, this is a recurrence plot in our paper. So if you can see, this is a high literacy student and this is a low literacy student. So at a glance, you can see we have more black dots in high literacy students, right? And then this is the excerpt. So you can see how students are using those math terms like multiply or equal to, and they are actually reasoning their answers, like because their ages have product of this. So they are like explaining what their thinking process in their discussions. But here, the low literacy students has less recurrence rate, as you can see. And then actually they are not really, they are very easy to be distracted. For example, they are talking about like, oh, the answer is C, and there's no reasoning. And then the student is talking about, oh, how's your freshman year going? So they are easily deviate from the main math discussion. Okay, so the time is up, but I have like 3 contributions. Yeah. So theoretical contribution, it can work as a grounding theory for linguistic synchrony, and methodological, this is like empirical data analysis using CRQA, and it could also work as like a automatic assessment of math literacy. And lastly, it can help teachers or educators to promote mathematical discussions. Thank you so much.